Let's see here. La la la. All right, we got it.
Hello.
I think we got it.
Hey, Jeff.
Let me begin with a word of prayer. I'll start. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask that you just bless our work today. Help us to glorify you in what we do and just understand more of your math together today, Lord. In your name I pray, Lord Jesus. Amen. So I have published for you guys, posted new notes, right? And so like at the end of chapter 4, I have added a section. And so let me just start by working through that. It's pretty simple. If you guys have already had linear algebra, this will be like, you know, totally unsurprising. Here we go. So if I have t of x comma y, right, and it's equal to ax plus by comma cx plus dy. First of all, my notation means that that is ax plus by cx plus dy, right? So my this means column vector, all right? And anyway, this can be written, of course, as a, b, c, d times xy, right? This right here is the so-called standard matrix for t, right? T, which is a mapping from R2 to R2. All right, that's a standard matrix, right? Example 1. What if we had t of x comma y equal to, oh, I don't know, x plus 2y, 3x plus 4y. All right, in that case, you can work it out, and what you get is 1, 2, 3, 4 times xy. All right? So there you go. The standard matrix of this linear transformation is 1, 2, 3, 4. All right? Show of hands, who's already looked at standard matrices and like linear algebra? Anybody not had linear algebra? This is totally new? Okay, good, good. So, you see, of course, we can think of R2 as being the complex number system, right? So there's a natural question to ask here, which is, what happens if you let the formula actually not just be a matrix multiplication, but multiplication by a complex number? All right, so definition, multiplication by a plus ib, all right? If that acts on x plus iy, that is by definition a plus ib times x plus iy. So this is left multiplication by the complex number a plus ib. This defines a mapping on the complex plane, or R2. Yeah?
When you say thinking of R2 as the complex plane,
I mean literally R2 is equal to the complex plane. Yeah.
as in like
A point set. A point set, as in a point set. So then if we multiply this here, we get ax minus by plus I times, you know, ay plus bx, right? And remember the notation, namely that 1 is equal to 1, 0, and I is equal to 0, 1, right? That's our standard nomenclature, if you will, for the complex numbers as they relate to R2. So putting that into practice here, this is really ax minus by, and that is really bx plus ay, written as a column vector. But then, since we know how to multiply matrices times columns, you can rewrite this as a minus b, a. All right? So, that's what the standard matrix of a mapping on the plane looks like if that mapping on the plane is achieved by multiplication by a complex number. Does every linear transformation on the plane look like this? Well, no, right? I mean, look at this. This one right here, 1, 2, 3, 4. Is that the same pattern as that? Certainly not, right? So if your mapping is defined by complex multiplication, it's a very special kind of map, all right? In particular, we could rewrite this right here as A plus BI and then minus B plus AI, using the interplay between complex numbers and two-dimensional column vectors, all right? We could write that. If you write that, you notice that what we have, the pattern here, is if this is Z, right, then this right here is IZ. All right? So so basically the section I added to the notes, guys, and the end of chapter 4 is just a very quick treatment of the linear algebra of the plane. So I defined standard matrix, and I even prove that the matrix, the standard matrix of a composite is the product of the standard matrices of the transformations composed. Is it big enough? I'll get it.
Might be.
Do. All right, cool. So these calculations I'm showing you here, I have a theorem that collects them all together and just makes a nice list of equivalent conditions for when a mapping on the plane, a linear transformation on the plane, is actually one of these multiplication by a complex number maps, right? So I give a definition for that here. All right. And my definition is right here. My definition is that, well, I just wrote that L sub alpha over there, right? But my definition is that if there exists a complex number, all right, for which the linear transformation is just the multiplication by that complex number, we're going to call such a map, quote unquote, complex linear. It's a complex linear map, all right? A complex linear map is a special kind of mapping on the plane, all right? And here's a list of equivalent conditions. T is complex linear. That's the definition. This right here is really crucial. A complex linear map is one where you can take a complex multiple of V and you can pull the complex number out. You can always pull a real number out of a linear transformation, but you can't pull a complex multiple out of a regular one. That, it turns out, is really the critical way to look at it from an abstract perspective. As I just showed you, the standard matrix looks like that, right? And by the way, do you guys remember the standard matrix? What's the other way to define the standard matrix from your linear algebra course? Remember the first column is the linear transformation acting on the first basis element, T of E1? Well, E1 for us is 1, so T of E1 is T of 1. This first column is T of 1, and that next one would be T of I. But T of I is equal to what, if we can pull I out? Right, T of I is equal to I times T of 1. Which means that the first and the second columns are related, right? In the sense of complex multiplication. They're not linearly dependent in the real sense, but they are linearly dependent in a complex sense. But anyway, let us not get into that. Okay, so, the double scrolling hasn't gotten me again. We jumped all the way past chapter 5. That's not good. So, in summary, yes, sir.
Maybe dumb question. Do we have access to this document as well?
I posted it in Canvas. I made an announcement. Did the announcement not go out? Okay. I mean, I would understand if you had turned off announcements, as it is university policy for us to make meaningless announcements in all of our courses. So, here's your start of the week announcement. Here's your middle of the week announcement. Here's your encouragement announcement. It's like, you know. So I try to only make announcements about, well, actual announcements. I don't know, like something actually happened. Usually it's a typo, right? Admittedly. So another way to look at what we're doing, let's just introduce this notation. M is a mapping that takes a complex number, x plus iy, and produces a 2 by 2 matrix, x minus y, yx. See that? That is the 2 by 2 matrix, which corresponds uniquely to the complex number x plus iy. From an it's like the perspective of abstract algebra, if you've had that, this is an isomorphism of algebras, right? Anyway, okay, so now that we've got that out, yes, sir?
Is it also a homeomorphism?
In what sense?
Topological?
I guess then the question is, what's the topology of matrices? If you'd like to know what the topology of matrices is, you should come take my advanced calculus course. We'll be doing that in about like next week. Anyway, okay, so yes, it is. It's in fact more than that. It's like, it preserves the notion, it's like more like an isometry or something, because the, well, hey, you're just, that is an evil. I will not chase that rabbit. I reject your rabbit. I refuse to follow it further. Let us go on. So that's it. That's all for chapter 4. I just want to show you this is what a special kind of linear mapping is. Corresponds to complex multiplication. That's going to play a major role in what I'm about to tell you. So what I'm about to tell you is the theory of complex differentiation. Anyway, so definition. Let me put the definition up here. Make sure I don't forget something. So if the limit as z goes to z naught of f of z minus f of z naught divided by z minus z naught exists, then we say f is complex differentiable. Complex differentiable at z naught, and write f prime of z naught, which you could also write as df dz at z naught, is equal to the limit that I just wrote, and I'm now writing again because I made bad life choices. I mean, if I could find a way to rewrite this sentence so I didn't have to write this limit twice, that would have been smarter. But, oh well. Does this look familiar to you? Do you guys remember Calculus 1? Yeah? You're good. I'm just going to adjust the zoom. There we go. Remember Calculus 1? This is the difference quotient definition, right? We used an x and an a, or an x plus h and a, x. Yes?
You also formulated the as x goes to a way where you'll have like z goes to h or something, and it'll be h on the bottom as opposed to z minus z naught.
Yeah, sure. You could make a substitution that this is the same. There's a substitution of limits theorem, which is true. You could do the limit as h goes to 0 of f of z naught plus h minus f of z naught divided by h. That would be equivalent, yeah. Now, also, we define the mapping z maps to f prime of z to be the derivative function, if you will. Derivative function for all such z as that exists, right? So, again, same as Calculus 1, right? Now, if f prime of z exists for some open set containing, let's say if it exists for some open disk centered at z naught, then f is holomorphic at z naught. And if the mapping is complex differentiable on an open set, then we say that the mapping is holomorphic. So like a mapping is holomorphic means that it's complex differentiable on an open set. So we talk about holomorphic with respect to a set usually, but we can talk about it with respect to a point with the understanding that means that close to the point you have complex differentiability, right?
As in on an open disk.
On some, there exists some open disk around the point, yeah. Now I think I had the good sense to make that definition later in this chapter. As you can see, I didn't put it here yet, but all right, so what can we do? Example 1. How about f of z equals to z squared, right?
This example 1, number 2.
Example, fine, yeah, thank you. It was example 1 of chapter 5, but I get your meaning. Okay, so this should be nostalgic. This should take you back to simpler times. F prime of z, and you know what? I will take Ben's suggestion and use the h formalism. All right, we could do limit as h goes to 0 of z plus h squared minus z squared over h. Now all my notes is all z naught formalism, but here we could do this. Fine, why not? It's logically equivalent. So then what? Well, you know, square it out, right? What happens? The z squareds, they cancel, right? And the h's reduce. We're left with the limit as h goes to 0 of 2z plus h, which equals, surprise, surprise, 2z, right? So let me summarize what we've just shown. We have shown that d dz of z squared, guess what, is equal to 2z. This is from the direct difference quotient definition of the complex derivative. Okay? Do you guys remember all of the proofs you did in Calculus 1 in terms of limits? You can do all of those here again. The cube, the single power, the reciprocal. You can prove the product rule. You can prove the quotient rule. You can prove the chain rule. All of those rules of calculus are proved in exactly the same way here in this definition, because the limit laws are the same, so you can go through the same proofs. I'm going to show you different proofs today because I think you should see something different. So I'm going to show you that there's another way of looking at complex differentiability invented by a fellow named Caratheodory. And I'm going to show you that there's another criteria. We can replace this with Caratheodory's version of differentiation. And I'll show you how we can prove the laws of calculus in that formalism, all right? But before I get there, let's do a little bit more. We should see something that's not complex differentiable, right? So something that's not complex differentiable, standard example would be, I'll do it over here. Well, you guys will remember this, right? I should have written some of that in some sort of, well, anyway, I can write it again. Well, I seem to not be coughing at the moment. That's good. I'll tell you what, though, when I cough today, I really, really cough. So that's just don't make me laugh. That would be bad. Okay, so example
7.
Don't do that. Example 3? No, is it 3? Okay, thank you. Thank you. Yeah. All right, f of z equals to z bar. All right, let's look at the derivative of this. So the derivative with respect to z of z bar, what's that defined to be? The limit, and I'm going to go back to my z naught formalism, okay guys? Z goes to z naught. Actually, my bad. I can't do that. I'm going to say this is, I'm trying to calculate. And so, you know, in some sense it's wrong to write this because we're going to soon learn that this doesn't exist. But if it's okay with you guys, let us adopt the convention we write f prime of z naught equals do not exist to express the fact that it doesn't exist, all right? All right, so this is supposed to be z bar minus z bar naught divided by z minus z naught. All right? What kind of limit is this? What is a complex limit? Well, it's a limit in the plane, right? What does it take for a limit in the plane to exist? Remember calculus 3? We have to have what? If you want to prove it doesn't exist, what do? You look for different paths that the path limits differ. So easy paths to think about here are like z equals to t versus z, my bad, I should say t plus z naught, I guess. Oh no, just a second guys. Oh, I've used a in the notes. It's fine. So z naught plus t versus z equals to, say, it plus z naught, right? So to graph what I'm talking about, these path limits are what? If this is z naught, right? Why? The stupidest possible place to write the z naught, right over here. So this would be this limit, right? This path. And again, poor choice of placement on my part. That would be this guy, right? So obviously different paths, right? And so to approach z naught, for both of these, we look at t goes to 0, right? So if we look at the limit as t goes to 0 of, let's see here, it plus z naught conjugate minus z bar naught divided by it plus z naught minus z naught, what do we get? Versus what happens if we look at the other path limit. See the difference? So remember that the complex conjugate of the sum is the sum of the complex conjugates, right? So this just simplifies to the limit as t goes to 0 of minus it over it. And the other one simplifies to the limit as t goes to 0 of t over t. So what do we get? Minus 1? 1. Right? So if we look at the difference quotient limit, we see that it is a limit which does not exist. Which points in the complex plane does it not exist?
Pretty much all.
Right, z naught's arbitrary here. So this shows that f of z equal to z bar is nowhere complex differentiable. All right? Are we good? All right, let me go on and then share with you the next. Let me try not to eat too much class time up on this, because the role that the theorem of Caratheodory plays for us is primarily just a proof thing. Like calculationally, I don't see us using this much past this point. It's a useful idea to prove theorems of calculus, but that's kind of as far as it goes. So the theorem of Caratheodory I'm about to share with you is a useful device for here, for proofs, but that's kind of as far as it goes. So maybe I shouldn't even write it on the board. Maybe we should just like read it together and think through it. That's probably a better idea. Because once I start writing things, bad things happen. So the idea of the theorem of Caratheodory is simple enough. So by the way, in the notes I have a few things I haven't covered in class, right? You should always read these notes. I can't say everything in class, right? As I said, enough suffering. On to greener. Do you enjoy this view? Do you enjoy the limit calculation way of doing it? I don't. Right? I don't. There's a better way. And here it is. So Caratheodory, I'll fix it.
Which one is it?
It's okay. I'll get it. Because if you touch it, there's this thing where if you accidentally hit the screen, then it opens up things, and it's just bad things happen.
Okay.
All right, so the theorem of Caratheodory it's actually very simple. It's an equivalent formulation of differentiation. You can do this in Calculus 1 too. When I teach Calculus 1, I actually teach this to Calculus 1 students. And they love it. They just love it. They're like, oh, please, more proofs in this course, or I just love proofs so much. Actually, that happened once, and that guy is a professor at Boston College now. But that is a somewhat exceptional case. All right, so the theorem of Caratheodory is that if you have a function which is complex differentiable at a point, that's true if and only if there exists a function which we could call the difference quotient function, phi, that has the following two properties. It's continuous at A, and what it does is the difference of f of z and A, it will return to you if you multiply z minus A times the Caratheodory function. So if you solve this for z not equal to A, it means that phi of z is what? It is the difference quotient, right? But I write it this way because, anyway, that's how I write it. So those two conditions are equivalent to the existence of the difference quotient. It doesn't seem like this is going to be much of an improvement, but it actually is a lot. So the proof is right here. If I assume that it's differentiable, I can define phi of z to be the difference quotient. I know that this limit exists, which implies that the limit as z goes to A of phi of z is equal to phi of A. And that is the derivative. So that's the one direction. And, oh, I'm sorry, I didn't mean to bring one direction into this lecture. Really trying to not do that. Anyway, so there's the proof of and then the other direction, if I have a phi which satisfies properties 1 and 2, well then that means that the difference quotient is equal to phi of z, and then the limit exists, so therefore it's complex differentiable. I mean, it doesn't seem like this should help you at all, does it? It's just stupid. It's like just giving a label, a notation for the difference quotient. But man, let me talk to you about what it does. It gives you a formula. See, it gives us a formula for f of z in terms of the difference quotient function. F of z is f of a plus phi f of z times z minus a, where this is a continuous function which limits to the value of the derivative at the point. Likewise for g. So if I want to find the product rule, what do? I multiply these approximating formulas. And when I multiply f of z times g of z, I get this. But then the thing is, I can factor out z minus a. Lo and behold, this serves the role of the Caratheodory function for the product. Then I take the limit as z goes to a. What happens? That goes to f prime of a, g of a. F of a, g prime of a. That limits to 0. Product rule. Product rule without limits. Product rule without adding 0. See, there's nothing clever here. I didn't add 0. In your proof in Calculus 1, you add 0. You do something really sneaky. You've been taught it, but it's sneaky. This is like just straight calculation. And then here's the proof of like the quotient rule. It's uglier, but here it is. Quotient rule is still true. There's the Caratheodory proof. And as I was saying, we can prove the laws of calculus. The derivative of the sum is the sum of the derivatives. You can pull constants out, and I'll probably make this a homework problem, prove the chain rule, all right? And so I would encourage you to prove the chain rule using like the Caratheodory approach. That just makes it easiest. But anyway. As you should know by now, if you get stuck on it, if you come ask me, I will tell you pretty much how to do it, right? Yep.
Does that imply the chain rule? Let's suppose W is equal to the conjugate of Z, at which point we know that dW dt is just straight up undefined. So if we can formulate a function as a function of the conjugate, does that imply then that that function's derivative will be undefined?
Well, I don't know, because this is only the chain rule for complex differentiable functions. So you're talking about something outside the universe of discourse. But the answer to your question is answered in the last section of this chapter, where I extend the theory of differentiation to functions of z-bar. This is known as the Wirtinger calculus. That's my last thing to talk about today.
I was going to say that, but I didn't want you to wrap.
Don't make me laugh. I already said this. Look, here's the proof. This is the proof of the derivative of z squared in the Caratheodory approach. We did the limit over there, right? Here's what the proof, the derivative of z squared is 2z in the Caratheodory approach. Here's my f of z. Now, admittedly, to find the phi of z thing, that's sometimes a little bit sneaky. So in that sense, like, I don't think Caratheodory is a good way to calculate derivatives. It's a wonderful way to prove theorems about derivatives. Like, because, you know, I add and subtract a squared, and then I'm like, oh, difference of squares, hooray! And then oh, look, so I've got f of a something, and then z minus a. That means that this something has got to be my Caratheodory function. Phi of z is z plus a by this identity, and then the limit as z goes to a is 2a. So a maps to 2a is the derivative, which means that the derivative of z squared is 2z, switching the a to z. And here's the derivative of z to the fourth in the language of Caratheodory. All right. Listen, you'll have a homework problem where I give you a relatively simple problem like the z cubed, and I'll ask you to calculate the derivative of z cubed from the limit definition, from the Caratheodory definition, and then from the theorem involving the Cauchy-Riemann equations, and then finally with the Wirtinger calculus. There is 4 equivalent ways we have to approach complex differentiation. I think that and they each serve their purpose, all right? So anyway, let me go on here. So we can prove the power rule for integers. If you sort through things, d dz of z to the n is n times z to the n minus 1. It turns out we can still say that that's true if we take a complex power, but then we have to be using a choice of the argument. We have to make a quote-unquote branch cut of the power function if we want to do that for a complex power. More on that. I'll make some homework problem that will help you understand that better, because we do need to think more about that. This approach has its limits. Pun partly intended. If you try to just, I'm going to differentiate e to the z, and then you try to do it in this kind of like either the direct definition or in the approach of Caratheodory, which is really the direct definition dressed up a little bit. I personally just get stopped dead in my tracks trying to directly calculate the difference quotient for the exponential. And I can do it. Oh, look, here's the Caratheodory function. It's e to the z minus 1 over z. But then take the limit, for example, as z goes to 0. I'm just trying to calculate the derivative at 0 for the exponential. That's a low-hanging goal. I mean, that's the first thing. So I'd have to prove that the limit of that as z goes to 0 is 1. I mean, it's true, but we just don't have the technology to prove that. I mean, there is a L'Hopital's rule, right? So, in fact, I was looking through my complex variables books to try to find homework exercises that would be good for the next set, right? And one of the problems I found was the proof of the L'Hopital's rule that one of you guys told me about in office hours, essentially. Yeah. Right. Yes. That is a deeper problem. Yeah, thank you. Okay, so I think I already defined this. We say f is holomorphic on a domain D if f is complex differentiable at each point in D. We say it's holomorphic at a point if there exists an open disk centered at Z0 on which the f restricted to that domain is holomorphic. All right, so if you put everything together, you see polynomials are holomorphic on C. Rational functions away from there where makes the denominator 0 holomorphic, right? But that's kind of about as far as we can go here, right? Because, yeah, it's about as far as we can go. It turns out that this function right here is complex differentiable on the coordinate axes. We're going to be able to prove that. But that's it, which means that while this function is complex differentiable on the coordinate axes, it's nowhere holomorphic, because to be holomorphic means you have to have like an open set around the point which is complex differentiable. And this function is merely complex differentiable on the coordinate axes alone. I don't want to prove that that's the case here. It becomes really easy with the next section. All right? Yeah.
So essentially from like an intuitive, complex differentiability is differentiability but like point-wise, and being holomorphic is complex differentiable but set-wise, essentially.
Something like that. I mean, to be holomorphic means that, again, you've got complex differentiability not just at the point but also nearby. So, yeah.
Whereas complex differentiability is defined on like points specifically.
Right. Yeah. So, I mean, I would say that the holomorphicity or holomorphic is a more interesting property. And listen, not all books agree on the terminology. Like the book that I wrote the notes from before, Gamelin, he would not use holomorphic in the way I'm using it. He would say analytic. The book that whoever taught complex last year, I forgot who it was, last year used Saff and Snyder, which is a popular book, wonderful book. They also call complex differentiable analytic. And there's a reason for that. But I think it's really more healthy to call it holomorphic, because when I think of analytic, that has a larger meaning. Like we say a function's analytic if it can be represented by a power series. That's true in the complex domain. It's also true in the real domain. Like, so the concept of analyticity is larger than this discussion. Holomorphic is special to complex variables. All right, so that's why I'm using this terminology. It is standard terminology, but okay. So next up, let f be. Finally, this section right here and the next one, these are the ones we actually want to use going forward to calculate examples. All right? In some sense, the course really starts right here. This is the start of the real complex variables. This is how we calculate. So Cauchy-Riemann equations for the complex function u plus iv, the Cauchy-Riemann equations are ux equals to vy and vy equals to minus, I'm sorry, uy equals to minus vx. I need to get glasses. All right? I'm just going to slow down here. Take a second. Let's look at the Jacobian matrix that we did last time. All right? What's the Jacobian matrix for f as a complex function? By the way, this whole thing I'm erasing right now will become stupidly easy in this section. So much easier than this. It was important for me to show you that, though, because you should appreciate what's being replaced. All right, so so if we have f equals to u plus iv, right? In the column notation, that's uv, right? So the Jacobian for f, right? Remember, it was partial f, partial x, partial f, partial y. What is that explicitly? In terms of the component functions, that is ux, vx, uy, vy. Right? These Cauchy-Riemann equations, What are they? The Cauchy-Riemann equations are ux equals to vy and vx equals to minus uy, right? Or you could say uy is equal to minus vx. I think I'm going to do that instead. Yep.
If anything, it's almost like you took del f del x and del f del y and put them in a complex number and then represented them as a matrix and then took out the equations from that matrix.
So what you're saying is, if I impose these equations, this looks like what? ux, right? And vx minus vx, right? In the big M notation I introduced at the end of chapter 4, this is the matrix representation of ux plus I times vx. Yeah.
Wouldn't it be u sub y instead of ux?
No. I mean, you could go that way if you want.
Because I mean, the Cauchy-Riemann equations.
What I'm trying to say is, you could also say, we could also say JF is equal to, like, get rid of the x's, keep the y's. So I've got Vy, take my Vx and replace it with a minus Uy, right? Uy, Vy, right? So in the matrix notation, that would be the matrix of what? Of Vy minus I Uy. That's also true.
I more mean, like, I understand how you got from the Cauchy-Riemann equations to the big M notation. Like, how did you go from the Jacobian matrix to the big M notation? Because that sort of colorful equality doesn't seem to make sense.
Why not? I'm imposing, I'm saying if the Cauchy-Riemann equations are true, this happens.
Okay.
Is that generally true? Of course not. There are many functions which do not have this pattern. For example, if we look at f of z equal to z bar, this is equal to x minus y. What is the Jacobian matrix of this? Partial derivative of this with respect to x, 1, 0. Partial derivative of this with respect to y, 0 minus 1. That is not a complex linear, that's not the matrix of a complex linear map. It's not the right pattern. Corresponding to the fact that this one does not have ux is not equal to vy, is it? See that? Ux is not equal to vy. See the f of z equals to z bar, the component functions of it, namely x and minus y, they don't solve the Cauchy-Riemann equations.
So what we're actually saying is we're imposing that condition and thus saying that the Cauchy-Riemann equations are precisely when the Jacobian is complex linear.
The Cauchy-Riemann equations are precisely when the Jacobian is complex linear. Yes, that is the point.
Okay.
We have theorems. So here they are. So these theorems are glorious because what they are going to do for us is free us of the drudgery of calculating limits. And we will enter into a sacred pact with partial derivatives. And we will use partial derivatives to calculate complex derivatives, which is our happy place, because you guys love calculating partial derivatives, right? You're like, whatever it takes to get rid of the limits, do that, right? Am I agreed? You guys agree. So this theorem says if it's complex differentiable, then the Jacobian is in the regular representation of the complex numbers. The proof, I use the Caratheodory expansion for the function, and I show that the Caratheodory function can be used to show that the Frechet quotient is satisfied, which then shows you that it is real differentiable. And since it's real differentiable, it has a Jacobian matrix, and that Jacobian matrix has the formula that's generated by f prime of z naught times h, which is to say that it's complex linear. Which then means we have the Cauchy-Riemann pattern. We have that the ux equals to vy and the vx is equal to minus uy. So that's the one direction. Oh, again, I seem to have brought them back in again. I'm very sorry about that. You notice though that this pattern, right? This pattern, that saying that this is complex linear means that the first, going through the details here, we find that the first column is f prime of z naught and the second column is I times f prime of z naught. What that means then is that partial f partial x is the derivative at z naught, the complex derivative at z naught, and partial f partial y is actually I times the complex derivative at z naught. In your homework this week, you should have seen these patterns in the functions that you differentiated, which were actually complex differentiable. I think most of your problems were, actually. So if you've seen these patterns already in your last homework, if you just were looking. And if you didn't see them yet, now you can go back and find them. So these two boxed equations are the Cauchy-Riemann equations. This is the Cauchy-Riemann equations at just the level of f notation. These are the Cauchy-Riemann equations at the component level. So both have their place, right? So anyway, a question? Yeah.
With del x x and del x y, we're okay with them acting on complex functions, even though we had originally defined them for real vector functions, right?
Say what you said again.
We're okay with the partial derivatives acting on complex functions, even though we had originally defined them for real functions.
In chapter 4, at the start, I defined the derivative of a complex valued function, partial derivatives there. So I gave definitions for this theory of complex differentiation back at the start of chapter 4. And we even have a proof of like the product rule there. Okay. Maybe I should make you guys prove another rule or two of it to appreciate it more, I guess. I don't know. But those are not terribly interesting proofs. They're just kind of like, you have a rule of calculus for real partial derivatives. And then if you're differentiating a complex valued function, you differentiate the real part and the imaginary part separately. And because the rules of calculus hold for the real part and the imaginary part, you put it together, they hold for the whole thing. That's the proof, like every time. But maybe that would be a nice homework, right? Actually. Okay, so here's that one I was just saying that I don't want to do in the limit approach, but it's simple here. See, this x cubed y squared plus y squared x squared y cubed. So here are the partial derivatives of the component functions. And the only way you can have ux equals to vy and vx equals to minus uy is if you have both x, if you either have x equal to 0 or if you have y equal to 0. The only way to solve the Cauchy-Riemann equations here is on the coordinate axes. And so there you go. This function is complex differentiable I think I can't say that yet. What I should say is this function is not complex differentiable away from the coordinate axes. That much I can say. See, the other side of this is, the next thing to ask, right, is what about if the Cauchy-Riemann equations hold, does that imply that you have complex differentiable? See, we went the other way. I said, we have complex differentiable. What does it say? Well, if we have complex differentiable, it says that the component functions must satisfy the Cauchy-Riemann equations. How about the other direction? Right? Well, that's what comes next here. So that is this theorem. If we have f is continuously differentiable, continuous differentiability, that's the thing I proved last time, right? If we have continuously differentiable on a domain D, then f is holomorphic on D if and only if the component functions satisfy the Cauchy-Riemann equations. So the forward implication we were just talking about, that was the proof with the Caratheodory thing I just went through. The reverse direction, the argument is this, all right? If you have continuous differentiability, that implies real differentiability, meaning that the Fauché quotient vanishes and there exists a differential. All right? But the differential, the formula for it, is given by what? It's given by the standard matrix times something, right? If the standard matrix, if the Cauchy-Riemann equations hold, then that standard matrix is in fact what? It's one of the, representations of the complex number systems. Excuse me. And then it follows that. Oh, I just ran out of steam. All right. I'm sorry, guys. I lost track of something. So if I've continuous differentiability, and I'm assuming Cauchy-Riemann equations hold, right? Then that means that my Jacobian matrix actually looks like this, right? Which then means that the differential is complex linear, like this. And then once I have all that, I propose that my complex derivative is that. So to show that the complex derivative exists, I chose to, so the complex derivative, I'm claiming the complex derivative is this. By the theorem I proved last time in the real differentiability, we have the limit of the Fauché quotient 0, right? But the arguments I'm about to give here show that you can take this and convert it to the regular difference quotient. Like so. So if I have that equals 0, it follows that this minus this must be equal to 0, provided that I know that this limit exists. In fact, I do, right? It's a plus ib. So if this limit exists and the limit of the difference is 0, it follows that that limit exists. And not just that, that limit has to be equal to this limit, which is exactly a plus ib. Voila, it's complex differentiable. So this is how Cauchy. So the critical thing, though, was that technical thing I proved last class, that continuous differentiability implies the existence of the differential and hence the satisfying of the Fauché quotient. Once I have that, then I can replace the formula for the differential with complex multiplication. That's essentially the proof. And then here, this is not necessary. This is already proved by the other theorem. But I just walked back through it one more time, the structure. And again, the Jacobian looks like this, which means it's one of these guys, which then means that the first column and the second column are related. Namely, that the second column is I times the first column. And more than that, the complex derivative is the x derivative if it exists, or minus I times the y derivative. But this assumes that it's complex differentiable. All right. So I'm going to come back to these things. Let me just let me finish the projectors part of this talk here, and then we'll do these things by hand. This is the Cauchy-Riemann equations in polar coordinates. I don't really care. You can skip the section if you want. It's just there because it's something I worked out, and it's in books, but I don't really care much about it. It is kind of convenient for doing the logs derivative, but whatever. The Wirtinger derivative formulation is something nefarious. It's bothered me. So you'll hear, you talk to physicists and they say things like, take z and z bar, independent variables. Does this bother you like it bothers me? Are z and z bar independent variables? Well, if you tell me z is 3 plus 2i, I know that z bar is 3 minus 2i. That doesn't seem independent to me, does it? And yet, there is a meaningful way in which we can talk about z and z bar as independent variables. That's what this section's about. So, first of all, using the derivatives of complex functions we talked about at the start of chapter 4, partial z partial x is 1, partial z partial I, partial y is I, partial z bar partial x is 1, partial z bar partial y is minus I. does everyone understand? Everyone should understand these. This should not be mysterious. This is just because z is x plus iy and z bar is x minus iy, all right? Great. So this right here I say is formal nonsense because technically speaking, it looks like I'm writing down a chain rule, but if you really search your heart and try to think about which functions I'm composing, you'll find out that this is not a chain rule in any meaningful sense of calculus. But nevertheless, it's something you might try to write down. Like, surely partial f partial x should be partial f partial z times partial z partial x, partial f partial z bar partial x, right? And, oh, well, this is 1, and that's 1. That's not hokey. I mean, that's just, we had that on the previous page, so we get that. And likewise, if I take I times partial f partial y, well, I got this chain rule, which gives me that. And if these two things are true, I can add these equations, or subtract these equations, and get that partial f partial z is this, and partial f partial z bar is that. All right? Now, this is not a derivation. I'm just giving you a plausibility explanation for why we make this definition. So we define the Wirtinger derivatives as these particular linear combinations of the real partial derivatives. That's it. That's the Wirtinger calculus. We work with these notations, partial z and partial z bar, which denote these particular linear combinations of the real partial derivatives with respect to x and y. It's just that. That's all it is. Yeah.
Could we instead try and formulate the Wirtinger calculus through like multiple complex variables like z and w, and then just sort of sneakily make w equal to z bar and sort of reduce it that way?
I don't know. Maybe. I really don't know. That's an interesting question. I just don't know. So once you accept my definitions, which aren't mine, right? Somebody else came up with them. Then you can easily check that partial z bar partial z is 0. And partial z bar is 0. And partial z is 1. And partial z bar is 1. So a person who just knew a little bit about calculus and was willing to just kind of do stuff could do calculations here and be right, right? If you have the idea that z and z bar are independent. What does independent variables mean? It means the partial derivative of that one variable with respect to the other one is 0. That's when are x and y independent? If partial y partial x is 0, and if partial x partial y is 0, they're independent. When are x and y not independent? Calculus 1, right? What do? Implicit differentiation. Y is a function of x, right? Are x and y always independent? Context, yeah. Anyway, and then of course, you can prove the rules of calculus. Why are these true? Because the partial z is built from a sum of partial x and partial y, and you have those rules for the x and y derivatives. The proofs are straightforward, but you know, I have to sleep, you know. So here's the proof of one of them. I can pull the constant out because we have that rule of calculus from chapter 4. And then if I pull it out of both, I get it out front, and then yay. So I'll probably give you guys one of the other things as a homework. That's an easy homework, right? Now, the Wirtinger calculus will also extend to chain rules of other natural calculations. Admittedly, Ben will ask me, but we haven't proved the derivative of cos squared yet, of a complex variable is a thing yet. And actually, I don't know how much trouble there is to really prove these things here. I'm just saying it's true. I haven't done the legwork to really prove that, but it is true. That is how it works. So finally, what's the point? The point is just this. If you have a function which is continuously differentiable on a domain D, f is holomorphic on the domain D if and only if partial f partial z bar is 0. So some of you have said this already. It's like a holomorphic function. It's just a function of z. It's not a function of z bar. This makes that idea precise. So if a holomorphic function is one which is not in any sense a function of z bar. You can also talk about anti-holomorphic functions. Those are ones which are just a function of z bar. And the proof is really, it's very, very simple. If we have continuously differentiable, then we already know it's continuously differentiable if and only if what? The Cauchy-Riemann equations hold.